Okay, so good evening, everyone. Let's start today's lecture. So first, about assignment 1, how many of you have not started? Which group? Who's not in a group yet? Actually, so everybody has at least 1 or 2 partners, so that you can stay afloat. Okay, so how many of you are facing difficulty with the assignment? Which question? Um, 26. Okay. So first question is easy, right?
We need to graph that out in Python, or we can just graph that by hand and then.
Yeah. Take a snap and put it in your document if you want. Yeah, that's fine. I think this is just hand computation. The second question, I said use backpropagation here, assuming you don't know the model parameters. Basically, you just need to do gradient descent, for which you need to know the gradient of the loss function here, the mean squared error, right? So you know what the gradient is, just a 2-dimensional vector. Yes.
Actually, for some of the question, we don't have data like the first one. Should we just
first one?
No, the second question 2.1. I mean, should we just submit like a word learning?
No, here you just need to write the function.
Write the function.
Yeah, just the def function. Def MSC with some arguments is equal to return something, right? Second one is it's saying plot the function. So you figure out how to plot it. I guess 3 should be 2, maybe, I don't know. So here you generate the data. So you need to figure out how to use numpy.random.random, or maybe random.random itself. And so you maybe learn about why there are 2 different random packages, sub-packages. This is the most interesting part, which is basically do gradient descent to figure out M and C, right? So here you actually know the gradient. It's just a 2-dimensional vector, right? You don't, even if you don't know anything about backpropagation, you should understand how to do gradient descent here, which is just find the gradient of the loss. Okay, maybe I should use. Let me just use here. So find the gradient of the loss. So loss here is sum up to n, I is equal to 1 to n of yi minus mxi minus c, right? So you basically need to find the gradient with respect to loss of the 2-dimensional vector. So let's say m and c are actually m and c essentially correspond to your if equivalent notation would be w and b, where w is just 1 cross 1 and b is just 1 cross 1. If you really want to think about it that way, it's not needed. Here you just need to find the gradient of L with respect to W or M, which is going to be just 1-dimensional, right? It's just going to be sum over I is equal to 1 to n of minus 2 xi of yi minus mxi minus c. Just take the derivative with respect to m and you will get this one number. You can compute this number at any given m. So typically, similarly, you will find the gradient with respect to c as well. There will not be a coefficient here. Okay, so xi's and yi's are constants. The only thing that you want to kind of update is m and c, right? From one value of m comma c to another value of m comma c. So similarly, you write another gradient equation, and then you will just update. For example, update of m would be m. Let's say at iteration t plus 1 would be just equal to m at time t, or iteration t minus some something else, step size or whatever, times the gradient of the loss at m is equal to m at step t. That's all. So you will need this because the gradient depends on the value of m, so you need to substitute some value of m. You're taking the gradient at m superscript t. So basically start with some random number, some number here, and find this gradient. This is the formula for the gradient. Actually, this is what you need to find using backprop. But you already know the answer. So if you do backprop, you know what exactly you should get. So it's just a kind of error check, right? And then keep running this for loop. Keep running it for every. Here. Yeah, you can do that. It's a constant. Yeah. If you want to, you can do that. I guess it's a mean square, so yeah, 1 by n. You can add. Yeah. So 1 by n. 2 by n. Yeah, this is it. This is the pretty much the solution. So I guess now assignment has reduced, so you don't need extension, right? Okay. Let's see. Yeah, and then there's a repetition. So now it's a 3-dimensional vector instead of 2-dimensional vector. There's m1, m2, and c. Okay, in 6. 7 is where there's a nonlinear transformation happening, and this is where you might want to kind of understand backprop. So backprop is really not needed for I guess 4, 5, 4, and 6, but 7 you probably want to use backprop. Otherwise, you can have the whole formula, where the right hand side is where is this? Where the right hand side instead of a simple thing here, it will be a tan h of mx plus c. So if you want to take a derivative, you kind of just have to follow chain rule. So backdrop is just chain rule, right? So when you're taking derivative of this with respect to m, you are actually applying chain rule. You're doing 2 times this thing plus the derivative of this thing. Times the derivative of this thing with respect to m. So that's why you got 2 times this plus the derivative of the coefficient, m itself, which is minus xi. That was chain rule. So backdrop is a different way to interpret the same thing. Okay. Yeah, and 3 is just write a function. 4 is basically trying to kind of clean up the previous, the example code that we have. So you actually need to do the string split, in part 2, and in part 4 you want to do actually cross validation to figure out the choice of parameters. Like if I think for the regularization we just took there was no coefficient in the example code. There was like 1/2 the 2 norm square of w. So instead of that, you might want to put some gamma there and maybe some coefficient there, and then do cross validation to check for that coefficient. Okay. How many of you are not following what I said? Which question? I said introduce the cross validation scheme, right? So what could be the things that you can change? The parameter is going to be the coefficient for L2 regularization, for example. Maybe the other parameters, maybe. Do you have any idea? Okay, step size, sure, you can choose step size. But that's a parameter for the optimization algorithm, not the model itself. But yeah. So you can change step sizes, the alpha that I wrote in the previous this thing here. You kind of can change this and see how your learning happens, gets affected. Where does it say that? No, exhaustive search procedure just means if you have a regularization parameter gamma, then you have to exhaustively try all parameters of gamma. So typically, let me write it. Let me write somewhere, next page maybe. Okay. So all I'm saying is you had a loss plus gamma times regularization. In this case, let's say it's 2 norm square of w, which just means some more ij wij square. Okay, if w is a matrix. I don't know if in this case, in this case it's a matrix. It's a multi-class logistic regression problem. So all I'm saying is this this is actually a continuous continuous parameter, but you can discretize, right? You can choose some very large grid. Like I'm gonna ensure that gamma is, I'm gonna search over 10 to the power minus 5, 10 to the power minus 4, all the way to 10 to the power, let's say 4 or something. So you have some 10 choices here. There are only 10 choices out of, and uncountably infinite number of choices for gamma. What I'm saying is this you need to exhaustively search in the sense of you need to put that number and see what the cross-validation accuracy is. That's a proxy for test performance. So for cross-validation, basically you need to just use the training data. So you should not be doing cross-validation in a jumbled way. So it's, we did a test train split, forget about the test, do the cross-validation, break the training data into parts, choose the choose the folds, all those are your choices, and try for all, for these different parameter values, which one is giving you the best performance. That's all.
Do you need to do cross-validation for testing like a nested
No, I don't know what you're talking about.
in the inner part that is like just use the data for hyperparameter for using cross-validation. So we also use cross-validation in the outside part,
For doing what? No, this is, I just said split the data into two parts with this percentage and just do that. So just cross-validation is just, you have these choices for your, maybe the regularization parameter. You just want to figure out which choice is good according to, you're basically, cross-validation is just to get a proxy for your expected square prediction error or whatever the equivalent is for classification. So it's basically called generalization error. I think some of you who have done previous course know. So it's just a way to choose one of the parameters. Okay. This gamma is called hyperparameter, and W's are just called parameters. Just naming convention. I think 4 is basically just cleaning up the code that was given to you in lecture 2. You see the attachments in the lecture 2 and kind of play with it. Yeah.
Actually, in question number 3, they asked us to report the prediction accuracy and training data and test data.
Yeah.
So actually, we train 2 parameters, one for training data, one for.
No, you just report this accuracy number for in-sample. I'm just asking for in-sample performance and out-of-sample performance.
But
so you get a model only using training data, and then you just kind of use the model on test data also to see how it works.
Yes, but that's the same as one question for us.
No. So here we got a number.
Yeah.
Here you're getting cross-validation accuracy. Cross-validation accuracy is only based on training data. Okay, now I'm telling the whole assignment. Now the stakes are higher. Okay. Now the grading would be tough. Okay. So I'm not sure if people have progressed up to this point, but I'm just saying that these are not difficult. Okay. Relative to, I guess, the previous course that you guys took, which is more difficult. So don't worry too much about it. So for example, 5 also is you base it off the code that I gave in lecture 2. Okay, so we already had the 2-layer feed-forward network code. So again, you need to once you've written the cross-validation, maybe it's a function, just call the function on this other model, which is the same gamma parameter that you kind of want to tweak. Now you may have 2 gamma parameters, so potentially. Okay. The tough part in 5, that's why maybe it's 25 points, is because there's a max of something and something, so this may require some thinking. Okay. So what is the gradient? What is the local gradient of this max operation? And I think we saw this actually for ReLU. We saw it was a gradient gate, right? So it's like a ReLU, but it has two arguments, max of a comma b. So you want to kind of understand what the local gradient is, maybe. Okay, and then here we are just using 6 is only about saying, okay, now you have your code base. Hopefully your code base is not too tailored to hard-coded numbers like 3 classes and number of observations. Then you can just change the x train, y train, x test, y test, and repeat with MNIST and CIFAR. Okay, and hopefully and you may require some pre-processing, may not require some pre-processing, depends on how you're acquiring this MNIST and CIFAR data sets. Okay, so maybe I should have said at the beginning that keep your code general, I guess. And then try to do the same with Keras. So Keras, you kind of saw how a feed-forward network and even a regular multiclass. I think we saw feed forward. A regular multiclass would be there is no nonlinearity, so there's just a dense layer. Okay. This. Yeah, exhaustive search is really just saying. I mean, otherwise, how will you figure out a good choice for the hyperparameter? So exhaustive search is just saying. Yeah, it's, you can ignore that line. Yeah, just do basically cross validation. There are 2 parameters, I think. Here, maybe? I'm not sure. Oh, okay, no, there's just one. Yeah, I don't know why it's requires.
One for the lambda, then again for the one CV again for the lambda, and the rest
Yeah.
then again for the lambda. That's why.
Okay, I mean, you can write the same answer, say C4. I mean, if you're convinced that it's the same question. Yeah, and 7 is, I'm not sure if this is the right link. Okay, yeah, so basically I showed ResNet. So basically VGG happens to be a much bigger weight, much bigger network. I think we saw, I think one of the slides showed that it had, I guess VGG 16 has 16 layers and VGG 19 has 19 layers. Both weights are available on Keras, so you just have to do Keras dot model, get this particular model. And what I guess the challenge here is to change the model so that you can use the same weights but to just predict on 5 classes rather than 1,000 classes. So that's going to be the change. So the last layer, I guess the first question is just use it on your data. So Keras is so this VGG 16 was trained on 1,000 categories, happens to have also cats and dogs, so you can easily so that's why even if you had cats and dogs, another set of cats and dogs data, you can use it with the ImageNet trained model. But I think the second one, so there's really no fine tuning. Second one is just saying just do transfer learning by, I guess, embedding. Just get the image embeddings and just do a simple linear classifier. Okay. So any questions? So VG's output is 1,000 dimensional, right? Final output actually, with probabilities. You can use them as feature vectors. You can also use the previous layer values as feature vectors in VGG. You just need to use that as feature vectors. Now you don't have any image particular problem. It's just a 1,000 dimensional feature vector and a label, 2 labels. So 2 class. It's just a simple 2 class problem. I don't know what 4.3 is, but yeah, it's a 2 class logic, 2 class classification problem. But now it's not image related or anything. It's simple class problem. Okay. For 2 class, the interesting thing is I don't know if you can reuse the code that you have. For 2 class, you have multi-class logistic regression. You can always do it for 2 class, but in literature or elsewhere, you might see that for 2 class logistic regression, the treatment is very different. There's only one set of p-dimensional parameters, some beta. That's all. In logistic regression, I don't know if you've seen it in 572. Some of you, if they did 2 class logistic regression, then they may have a single parameter vector p. If they're looking for if you had p-dimensional input vectors, and you only had one p-dimensional parameter vector, but we are looking at, so if you reuse the code, then you'll have 2 p-dimensional parameter vectors. So there is some over parameterization. Okay, so you'll get 2 scores instead of 1. So you can think about this. Okay, it's not there's nothing hard. I'm just saying I'm trying to reconcile. You should not be dumbfounded that why is there only 1 vector in 2 class setting versus 3 vectors for 3 class setting. 3 vectors for 3 class setting makes sense, but 2 classes because of some redundancy, probabilities have to add up to 1, so that's why you kind of get rid of 1 row. Okay. Okay. So no extension needed, right? Depends on the progress. I mean, there's one more week. So 1 week left. So so it'll be unfair to people who have already finished the. No, whatever. Whoever has finished, so they can email me their solution. Okay, and whoever has not finished, you can take 1 more week. So we'll add. So instead of Feb 20, I guess Feb 27th. Okay, same time. But whoever finished, you don't have to wait till that time. You can tell me beforehand. As in, if you can finish before Feb 20, just let me know, because it will be unfair that you finished it and other people are still working on it. That's fine. Okay. So now let's get back to today's topic. So actually, last time we kind of didn't touch Word2Vec particular implementation. We'll get back to that maybe like 2 lectures from now. Okay, when I'm gonna just round up deep learning. So next lecture we'll try to look at some unsupervised learning tasks. So far we have been kind of focusing on supervised learning, classification mainly actually. Today we'll look at a slight variation of supervised learning, and then next class hopefully we'll touch some recent advances in unsupervised learning, and then last lecture we'll just round up on some recent extensions and advances. Okay, so today we're going to look at recurrent neural networks and long short-term memory based recurrent neural networks, and sequence to sequence learning, or basically recurrent neural networks. Where are they used? Generally these class of problems are called sequence to sequence learning problems. Okay, actually the hyphen should not be here, it should be here. Long short-term memory. Okay, so let's start. So it may seem like recurrent neural network seems like a very different beast, but it's not really the case. Let's try to understand why we want to motivate another model. Okay, so it's basically captured with the idea of persistence. So people who have already seen this and probably already seen time series type of models will find this analogy kind of not very useful, but just let's go with this view, and then we'll reconcile with what we already know in terms of time series or other dependent. There's some temporal dependence or something like that. We'll kind of reconcile with that what we already know. Okay, so here basically the motivation is just humans have persistence, right? What we kind of infer about what we are seeing or hearing or something else doesn't just depend on what we are doing, what we are seeing or hearing right now, but also depends on a lot of other things. Maybe things that happened 10 years ago, or the things that happened 1 week ago. Okay, so there's a lot of persistence in our internal classification or internal recognition stuff that we are doing, right? So we understand the present given what we have seen in the past. I think there's an example where 2 Pokemon characters are fighting, and so there's 2 images where in one image one of the Pokemon is getting hit with water. Okay, so if you did not know, if you only saw the second image, you would think that the Pokemon is just taking a shower or something, but that's not the case. Right? So that's what I just mean by there's some dependence, or there's some persistence. Feed-forward neural networks, and CNNs are essentially creatures which only are kind of non-linear models looking at supervised learning. And typically in supervised learning, you're saying, okay, xi has some relation to yi. We are trying to find a map between them, and the map happens to be given by this feed-forward network or CNN. Now, maybe yi should depend on not just xi, but maybe the data itself has some order relationship, and maybe it should depend on xi minus 10, xi minus 5, and so on. So there is some previous data that also probably affects what you predict now. Okay. So it's unclear how a CNN can use information from previous scenes. So and at this point you can say, okay, if really there was information in previous scenes of, let's say, a movie that kind of help you predict something now, then maybe you should just concatenate all that. That's your huge feature dimensional vector, and that can be your, that can always be the case, and then you can make predictions. That is true. You can always make a concatenated vector and use that as a feature vector. But there are some, I guess, more interesting ways to not just concatenate and do something else. Okay, so that's going to be the theme for why recurrent neural network. Okay, because for example, maybe xi minus 10 and xi minus 5 have information related to the current prediction that you want to make, which is yi, but xi minus 9 and I minus 8 and so on are irrelevant. Okay, maybe in the scene there is like 2 frames where there's where somebody shows a person with a gun, who probably is a murder suspect, but in between there's some other dialogues and so on. So you don't have to use that as a feature vector. What I'm saying is there may be some selective parts of the previous information that may be important for your prediction. So anyway, so given that we want to kind of capture persistence, the architectures, neural network based architectures which kind of try to capture this persistence idea are generally given the name recurrent neural networks, and they are basically just networks with loops, that try to persist fast information. And how do they do that? So let's just kind of internalize this picture first, and then I'm gonna kind of tell you that it's nothing, it's just a representation. So it's a network. So things that are kind of obvious is, let's say xt is the teeth input in order. Okay, I don't want to just say time. It can be time, it can be something else, whatever. It's data order data. So let's say it's a teeth input. It goes into a box. Okay, and you'll see that it's just a neural network, regular feed forward network, for example. And but this network actually outputs 2 things. Okay, actually just one thing, but okay, so it outputs one thing, which is ht. So I'm using h because it's going to be related to hidden values, hidden vector, I guess the activation vector, right? So at time t, I gave an input xt and I got an output ht. And there's also some information that is passed on to the next time step processing. Okay, so that's why there's this loop here, which is trying to say, okay, I did some computation now, but I'm gonna try to pass it on to maybe xt plus 1th time periods computation. Okay, that's roughly the idea with this diagram.
So
Yeah.
this xt will be only one feature input, meaning all the input instances which are related to each other.
No. xt is your regular. You had, let's say, a movie sequence. A video. It's a sequence of images. So xt may be the teeth frame. So actually, I'll give some examples later. But so xt is your regular feature vector. Just it's subscripted by t instead of I. That's all. So it looks like A has 2 outputs and 2 inputs. A does have 2 inputs, but it's really not 2 outputs, and that you can see by looking at what is called an unroll diagram. Okay, this is just a shorthand, maybe a little bit confusing, but it's just shorthand for drawing A multiple times. Okay, so A still has 2 outputs and 2 inputs at any given point of, I guess, time. So this is the unrolled version of this diagram. Okay, so A is still a block, potentially a neural network, and given at current time t, there is an output ht, but that depends on not just the current time period input, but also maybe previous time periods some computation. Okay, and previous time periods computation is also remembered using the, I guess, 2 periods before computation. Okay. And here I'm just saying it could be, these x can be feature vectors, could be images, could be words in a sentence, and so on.
How is it 2 outputs?
Yeah, you'll see that it's really not two outputs, it's just the output of an activation. And I'll actually, next slide, I'll show that. Yeah. Speech, yeah, so speech, what you need to do is, I don't know, how many of you have actually dabbled anything with speech? None of you? Some of you? Anybody has dabbled with speech data sets? So when your mic captures speech, so it's going to be some temporal data, right? So, I mean, you can visualize this as a temporal data. You can also have a frequency domain representation of this data at every short. So you have a temporal data like some time series. You can take parts of it, like 100 observations and so on. And for that, you do something called a Fourier transform, variation of Fourier transform. Get a frequency domain representation. Okay, a slightly more I guess more popular a variation of this is called MEL frequency MFCC version of this Fourier transform that I mentioned. So basically, what I'm saying is you have temporal data, you chunk it, you get vectors which are MFCC feature vectors, and then these are your XTs. That's all. So you have a sequence of vectors, but the initial pre-processing that you do is kind of you just chunk. Yeah. We may discuss. I mean, we may again slightly just get to this towards the end of this lecture. Okay, so there are two questions now, because he asked a question. So what are these two inputs, two outputs? Okay. And how is the block taking in two inputs? So in this slide, I'm just going to say that the key point is that all these blocks will have the same parameter. So there's the same parameter theta, which is affecting this box, this box, and all these boxes. Okay. What is this box doing? It's a function, right? It has two inputs and two outputs. So it's a function that we have not kind of seen predominantly before. We were looking at only functions which map inputs to outputs, so single input, single output type of functions. But it's fine. So it says two inputs and two outputs. But actually, yeah. Okay. So this box. So I'm going to call something a vanilla RNN if this box is represented with a particular thing called if it has a single hidden layer and a tanh nonlinearity. And so this is just I'm introducing a nomenclature, vanilla RNN, to say that there's one hidden layer in this box, this function. So this function is now represented as a neural net type of a object, and they use tanh nonlinearity. And to kind of show the box, it's too much of suspense. To show the box, I'm going to use some convention. A neural net layer is represented as a yellow box. Vector is going to be represented. Vector going from something to something, a box to another box type of object is going to be a vector. This is going to be interesting. This is going to be a concatenation operation, which means that if I have a vector x1, x2, okay, let me not use x's. Let's say 1, 2, and another vector 3, 4. Then concatenation just means 1, 2, 3, 4. Okay. And copy is just copy. So given that, so this is the vanilla RNN. Okay. The A box is nothing but two vectors getting concatenated, passing through a tanh nonlinearity. So here there's a vector. So there's one layer of neural network, which means that there's a vector. Let me write it this way. So there's this tanh of W of vector is going to be ht minus 1 and xt plus b. Okay, that's the operation which is represented in the blue in the yellow part, and that produces one output, right? That output is going to be the number of rows of the W matrix, the parameter, right? This guy, and that output is fed to the next guy as well as given out right now at this step. Okay, so this is it. So the parameters are going to be W and B. So theta in the previous slide was just W and B. Okay, a matrix and a vector. And the internal representation of each block is, so each block, if I unroll this diagram, let's say 10 times, then I have 10 such neural nets, right? 10 such hidden layers. All the layers have the same weights. In the sense of I'm not gonna allow different weights settings at different blocks. Okay, they all will have the same weights. Did we see this before? Yeah, we saw this in feature sharing, right? So sorry, what is it called? Parameter sharing in convolutional neural networks. So the filter weights were shared across multiple neurons, right? So multiple neurons were using the same weights. Here, neurons across different blocks will use the same weights. In fact, the whole layer will use the same weight matrix. Okay. Just an analogy. So in this vanilla RNN, there's just two parameters, W and B. Output is actually really just copy. So it's really not two outputs. So this is also HT, actually going to the next type. And each block you kind of are taking HT and XT, concatenating them and passing it through your nonlinearity. Yeah.
And is there a reason why we use RNNs here, RNNs nonlinearity function? Because for every RNN and LSTM, they always go with RNNs. So is there any reason for it?
No.
Can we play something else?
You can change it if you want.
But then,
I mean, there is no I mean, people have used I guess the name vanilla RNN to represent this, but you can define your own architecture. It's fine. There's no particular reason. The same reasoning that we had for all these nonlinearities in feed-forward network, the same type of reasoning about it being zero-centered compared to sigmoid, things like that. Otherwise, it still has issues, right? Saturation issues. So you can change it if you want. So, I mean, the idea is that somehow whatever computation is happening, let's say in a 10 level, I guess a 10 step unrolled RNN is going to be that maybe at the 10th step you want to kind of classify, or kind of predict who's the murderer, who's the murderer. Then you kind of have to kind of pass information about what's happening in the previous steps. Okay. Somehow the weights have to be configured such that they kind of pick on those features or those features in images which kind of let you make the right prediction. I mean, of course, you'll have training data where you'll have short snippets of videos with who's the murderer. You need to have tons of such data to actually kind of get the right weights. But that's the idea. Okay.
Is the same neural network that is working across different
Yeah, it's the same WMD. Yeah. The same. It's not the same neural network. So it's actually.
Is it copies of neural networks or the same neural network that do different
I mean, if you copy it, it's the same weights. It's as if there's a weight matrix. You're just reading the same weight matrix when computing. So if you do a forward computation, you just do clearly you just use the same weights. It's not like you copy anything and call different layers. It's a layer, right? So it's W matrix. You get to decide the number of rows of the W matrix, which is the dimensionality of this hidden, this activation vector. It's hidden because it's just use the notation from feed-forward network. So you can consider them as outputs as well. So this dimensionality is the dimensionality of the layer here. Okay. So the number of rows of W is going to be that dimensionality, and number of columns of W would be the dimensionality of this plus dimensionality of this. This times this. That's a vector. Any other question? The notion of it's not like there's information being stored, and it's not like there's a memory here. Okay, so this is another thing which I guess you'll realize later. There's no there is a persistence of information, but there is no explicit memory, as in nobody is writing to a disk or nobody is storing some information somewhere. Okay, it's just it's an elongated one-shot single neural network actually. It's just that there is some. It's like if you kind of analogy is time series model. You kind of have some parameters related to previous data points, right? That's all. That's what it is. So yeah, so this is just now that you guys are a little bit more familiar with Python. So here I'm just kind of showing how you may write an RNN. So basically, in this case, the vanilla RNN, you would have a length, the length of the activation or the layer inside the A block, and the length of the input. You have here you're just initializing the H's to be 0, because initially you need to, even the first A block needs to have some input, right? Because you define it generically. W and bias are just this matrix that I just mentioned, and this vector. And then here I'm just calling a step function which will step through, it will just do the W times H stack np dot dot. You probably have seen this in the 2 example codes, so you should understand what np dot dot means. Np is just a short form for numpy, right? So it's basically doing what I wrote in the previous slide, and then you're passing through nonlinearity, and that's the H value that you're storing, and you can return the H value as well. What is what?
X stack.
It concatenates the H with I mean, why it's a H stack and not a V stack, you kind of figure it out yourself. Okay. Yeah, so here, I mean, in code, there's actually a memory in the sense of we are remembering explicitly, but yeah. Okay. So in the last class, we described what is called a character level language model. So language model just has to predict what is the probability of the next word given whatever you have seen so far, and so on. So we can do the same thing. So last time I mentioned something called a Markov language model, right? It was just trying to remember, relative conditional frequencies. Like I've seen HE, what is the probability of seeing L? All the data set, just see whenever you saw HE and then the next letter L, you normalize it, and that would be your probability of seeing L given HE. And so from such a conditional distribution, you just draw the next character. Okay. So here you have to actually do something similar. Okay. And this I've already said, we generate, one of the, I guess, fun uses of language model is to just generate data. You can use language models to do other things. They are actually part of a key part of speech to text. So if you used Siri or Cortana or any of these things, language models are very important to have the right speech to text transcription, or to understand what you're saying, basically. So let's again kind of just look at an example of how an RNN may work with this. The RNN, what you need to think of, this is block, right? Inputs, H's, inputs XTs, X1 to XTs, and outputs, H1s to HT. So let's assume we have a vocabulary of just 4 letters, H, E, and L, and O, okay? And a training sequence is just, focus on one training data point here, H, E, L, L, O. And since it's a language model, it's actually unsupervised. There's no label, but but our data actually, we are creating what the label is. So given HE, we should say L, right? Roughly. So we have 4 training examples. Given H, I need to say E, right? And given HE, I should say L, and so on. Okay. And so we'll also use some very naive embeddings. So if you remember from last lecture, what an embedding is, it's just a vector representation for a symbolic thing. Here the symbols are H, E, L, and O. So we need vector representations for them. So we'll use, since there are 4 characters, we'll really kind of use four-dimensional vectors. If you remember, the whole point of last lecture was if we have a 100,000 dimensional English vocabulary, 100,000 words in the English vocabulary, we can encode them in 300 dimensional vectors, for example. So because we are, because we can kind of, that's not the big thing, but if you did just one-hot encoding, you would really be encoding them in 100,000 dimensional vector space, which is quite inefficient. There is no relation between words. With embeddings that we saw last lecture, the whole point was to have some relationship between words. So although we use lower dimensional space, words were somehow related with each other. Okay. Okay, so let's assume so our embeddings are going to be very trivial here. 1 0 0 0 0 1 0 0 0 0 0 1 sorry 0 1 0 0 0 1 0 and this and same thing for L again. So our input and output, so now I'm defining input and output given this word HELLO is going to be H, so our output is going to be O, E, and similarly the other ones. Okay, and so output is going to be 4-dimensional because our vocabulary size is 4-dimensional. So you can imagine, so just to extrapolate, if we were doing, maybe we were using RNN for predicting next words in the English language, or completing some sentences, so on. Their output space is actually potentially 100,000 dimensional because they really need to pick a word in the whole English vocabulary. Okay, so it's huge. So here we want to interpret the output as we want to ensure that the output vectors are such that if the true label is E, then we just want to have the score for the true label, the score corresponding to the true label be high. Okay, so we want to set. So here I'm just showing the values of the hidden layers, so the activations. Okay, so these three numbers happen to be the output of a tan H of some weight vector times this input, which is 1 0 0 0 plus a bias. Okay, so I guess these numbers are not very important in the center, but what I'm saying is I need to now tweak the W and H such that I ensure that if the true label is E, this score is high. If the true label is L, then this score is high. In this case, it's not higher than the rest, for example, right? And so on. Okay, so that's my training problem here. I want to maximize these core values. Okay, so we can actually just use cross entropy. Okay, but we'll do cross entropy across the 4 outputs. What do I mean by that? If you remember, in multi-class, logistic regression or even feed-forward network, we had a cross entropy loss function defined, right? So here we actually have 4 score vectors for one training data, which is hello, that word. We have 4 score vectors instead of 1 score vector. So we are just saying let's add the cross entropy terms across these four score vectors. Okay, so there will be 1 term per score vector. Okay, minus log the probability of the true label is going to be some renormalized version of the score vector, right? So there will be 4 terms, so I'll just add them up, and so that's my loss. Now I just need to propagate gradients. Did I mention that next time?
So what would be the dimension of the
Loss
loss vector?
vector. Loss is just one number.
Like before we average it, like before.
There are 4 terms. I mean, for this example, there are going to be 4 terms. Yeah, each term is just a minus log of the e to the power score of true label divided by sum of e to the power scores of all coordinates, 4 coordinates. I don't know do you guys remember what cross entropy loss is? You should probably, because it's part of your assignment. So the only difference is I'm saying there are 4 terms instead of 1 cross entropy term that you see in regular classification. That's all. And yeah, and you need to back propagate. I'm just seeing if I mentioned this somewhere. Okay, I'm just going to mention it here itself. So when you backprop, you need to just take care that there's a W matrix here. This is the same W matrix here, the same W matrix here, and the same W matrix here. So when you backprop through this computational graph, something is getting computed to some other output, right? For the current W's and B's. Okay. Now you need to backprop the gradient at the current values to these guys. But they're all the same, so you need to add gradients in some way. That's what at least the software does. You don't have to do it by hand. But what I'm saying is you need to. So for example, there's an output here, score vector. This did get influenced by this input, right? There's a path some computation happened here, some computation happened here, something happened here, something happened here, and something came out, right? And then this got transformed to get a loss value. So you need to pass the gradients till here to get a gradient, to get a gradient here. But same thing till here, same thing till here, same thing till here. So this one will only influence this guy, but this, these three losses will also influence this guy. I'm saying you need to aggregate those things. I need to aggregate, and since it's the same weight vector, you also need to aggregate the gradients. That's all. So some gradient aggregation needs to be done. That's all. I mean, if you have kind of understood how gradient aggregation needs to be done for CNN parameter sharing, because the filter weights are the same thing for all the neurons. So when you get backprop, when you do backprop at a slice, at one of the slices, all the neurons are using the same weight. So you kind of have to kind of aggregate the gradients. Okay, you're not doing that explicitly in any of your exercises or anything, but you need to kind of remember that. Maybe this is an exam question. I need to remember to put it in an exam question. Okay. Yeah, so I guess, and what is the issue of persistence here is just the same, saying that when the first time L is output, the next character should be L. Next second time L is output, the next character should be O. So there's output depends on what happened previously. Okay, that's kind of very simple example of persistence in this RNN implementation. Okay. So this is just a slide to kind of categorize tasks. These are your regular classification tasks. So there is mapping from xi to yi, and there is no relation of xi to xj. So you can permute your data. For example, when you're doing test train split, if somebody gives you data, it's a good idea to actually permute the data first and then do a test train split. Okay, because if there was any weak temporal, like somebody was making measurements and then they got sleepy and were making some other measurements, then the data quality will be different. Okay, so you want to kind of permute it and then split it into test train. So order doesn't matter. Okay, here, so these are all problems where you have a repetition here. So, things are going, but there's persistence, and this is a problem. For example, image captioning is a problem where input is an image and the output is the caption for that image. Okay, so if you see somebody hitting a ball in soccer, then there has to be captions saying that this is the penalty kick or something like that, right? This is first of all soccer, things like that. Now this is when you have this is actually something that we've already seen somewhat. For example, sentence classification. So sentence can be variable length. You want to just say whether the sentence was positive or negative or something like that, sentiment analysis. Okay, so the input is variable length. So here you can use RNNs. Sometimes you can also have variable length input, variable length output. So this would be literally machine translation. So you get an English sentence in and a Spanish sentence out. Okay, and this would be your same thing, but not now it's aligned. You can have a output at every same time step. So for example, here, it could be just video classification. So frames are related to each other. There's time series type of a setting. Okay. Any questions at this point? Oh, what's the time? Okay, so it's good. So let's take a 10-minute break and let's resume. Okay.
Regarding the dimension that you have used while training, for example, when you are using hello,
yeah,
right? I mean, decided the dimensions to be 4. So does that depend upon the training
vocabulary
example?
size? Yeah.
So that would depend upon the training data that you have taken, right? I mean, for example, if you have so suppose if you have they and the, right? So whether after E you get a Y or you don't get anything would depend upon how many times you get the in the training data and they in the training data, or how does it depend on?
No, which dimensions are you talking about? Output dimensions are vocabulary size. Output
Yeah.
dimension, the
Yeah.
score vector size, the vocabulary size.
Yeah.
Input vector, these vectors are just the embedding size. If you use one-hot encoding, you have to have the vector size to be the same as vocabulary size. If you use the word embeddings that we talked about, then it's going to be 300 dimensional, for example.
Okay.
You're asking now about 4 here.
Yeah, yeah.
Why is it repeated 4 times?
No, I mean,
or no?
is it because it has H, E, L, N, O? No, is that not?
Yeah,
reason
so the
why?
word length is 5 here, and
Yeah.
that's why there are 4 repetitions.
Yeah.
So I've clarified 3 things, right? One is input dimension is determined by embeddings, output dimension is determined by vocabulary size,
Okay.
and the number of unrolling is determined by the input sequence length.
Yeah. So the vocab size is what I'm talking about. I mean, what determines that? Is it the
Number of words that you want to consider, not just in the training, but also in the while, wherever you're going to use,
Okay.
right?
So
Embedding means, I'm sorry, just saying
Yeah.
the topic. So embedding means duplicated vectors into a matrix, right?
Embedding means those. Remember, there was this. I could have. So this is one-hot embedding. This is called a one-hot embedding. When you have one coordinate of the vector being 1 for if the character or the word is present.
yeah.
Right?
Yeah.
Instead of one-hot encoding requires the same number of same vector size as the vocabulary size. But
Yeah.
you don't need to use that. You could actually have input layer length just 2-dimensional, where you can put two numbers, arbitrary numbers, not hopefully arbitrary, but some 2 numbers, and you can have a shrinkage in the input dimension.
Yeah.
And that was the whole point of word embedding last lecture, which was saying that if you use contextual information, if you just want the words to be close to each other because of the contextual information, like cat and dog word vectors to be close to each other, they don't have to be one-hot encoded, because if they're one-hot encoded, they're not close to each other. They always have a distance of 2, because the dog will have a 1 somewhere else, cat will have a 1 somewhere else, so distance is going to be 2. Okay, but in 300 dimensions, there will be a bunch of numbers for both words and both dog and cat, such that their Euclidean distance could be small. That was the whole point of embedding. So you can only restrict yourself to 300 dimension, irrespective of whether the English vocabulary is 100,000 dimensional or 50,000 dimensional, right?
Yeah, so
That was
embedding
the-
is a kind of measurement of the distance between
They
just,
capture
vector,
contextual characteristics of the words. They put words into see, every embedding is all about a word and symbol. You get a vector out of it, vector for a word, right?
Right, yeah.
But word embeddings are good if those vector embeddings kind of capture some semantic information about the words,
Right,
that
right.
these words occur in similar
Yeah,
contexts.
right.
That was the idea last time.
Okay, so the embedding is a tool to transfer a vocabulary into a matrix.
Transfer
We
a
can-
symbol to a vector. Yeah.
So we can put into the
Yeah,
computation
yeah,
like
yeah,
image,
yeah.
those stuff.
Yeah,
Right,
images
just
are, we are assuming the
Like the
numbers.
RGB stuff,
Yeah.
methodology is just
Yeah, yeah,
similar to that.
Yeah.
Okay, understand. So you mentioned this W and B is the same, it's unified. Which
the
means,
same,
which
for
means
all of them.
my understanding you said is aggregation means every time you run through this model, use a back propagation, because WB you need to use the back propagation to
When you
maximize,
update.
right?
Yeah.
Lower the loss
Yeah.
to find the better one.
Yeah.
So you have so it goes through this is the cycle, right? You got this one, right?
Yeah,
That runs
you
through
get a
this
loss
one.
value here,
and
you
this
get a
is
loss value
this
here.
minimum loss, so you can move on, right? To here, right? You got here, but
No. This has nothing to do with this. So this is the training data. I mean, it is.
Right.
It is. I mean, this is just shifted version, like hello and HELL.
Sounds like you need to start from here, right? This is
Here
first
I'm just inputting all 4 here.
Okay, all
I
4
want to
here.
ensure that all 4 here are ELLO. So there's
Okay.
no. I mean, this is just a static thing. There's no storage. I mean,
Right. So, but to your point,
Yeah.
W and B is unified. So all the
Yeah, it's the
WB
same
is the
weight.
same.
Yeah.
Has to be same based
Yeah,
on this model
yeah,
structure.
yeah.
And you said the aggregation is
So that's why
you
you
have
need
to
to take
consider
gradients. Yeah.
all of them.
That's
to
why when you back
maximize.
propagate, you need to add gradients together. So
Add
whenever you have
gradient.
the same
You
parameter,
mean add is plus,
yeah,
just plus.
literally add.
Oh, okay.
Yeah,
Alright, so
aggregate
that
this
is-
is literally add
that is-
gradients,
okay.
because let's say you consider them different, then you'd have different gradients coming up to that point. All I'm saying is because those weights are the same, you need to add these gradients.
So the backpropagation methodology is happened simultaneously for all of those streams.
Yes.
And so then aggregation together to find the best value to minimize the loss for all of them.
Yeah.
Okay, got it.
But the issue with what I said is that you can backpropagate up to this point, but you also have to backpropagate all the way to this point, because here also W was used in the computation. So like the loss here depends not just on W used here,
but also
also
back
W
to
used
this
here,
here.
W used here, W used there. So
but this loss is not regarding to here, because
no,
of the
this
sequence.
loss depends on this 3.
Right,
this
but
loss depends
not
only
here.
one. No.
Okay, got it.
So the direction of the arrows kind of show that.
Wow, sounds complex. I mean,
It's
from
complex
coding,
to understand,
a lot of
but
computation.
coding people have already written, like Google TensorFlow has already written it. So you just need to know that this is how it happens.
Yeah.
Because if you want to debug it and you're getting all 0 values of garbage, then you at least need to understand what's the thing messing up.
I'm sorry for taking it.
No,
Just,
that's all right.
just like in your assignment, you code a term like exhaustive search.
Exhaustive search just means if you have a parameter, you need to try all the different
Do our
choices.
due diligence do that, or is that like a greatest? Because I know there is some like grid search, right? You can put some
With
things. Grid search function about like setup parameter in Python.
I don't know.
It's
I mean, I
easier.
know, but I don't know exactly what it does.
But because your code is super long, so we have to test, right? So do you mean that it's a
No, greedy search. No, exhaustive search means you need to, in cross-validation, you need to try different parameters.
Try different
exhaustively,
parameters.
yeah.
But I need to show you the process, so I have to copy.
No.
Oh, so just find the best.
Yeah. Find the best using exhaustive search.
But we have to change it, right? Because simply
You will write a for loop. If you have 10 options.
for loops.
Yeah. For all these 10 options, find me the best.
Well, but you have a lot of different parameters.
No, just one parameter. Regularization parameter is just one.
No, is there?
You're only trying to figure
you
out.
have W, you have B.
W and B
you
are
have
not. W and B are.
regularization. You have steps. You have.
No. Only regularization parameter is what you need to do.
Just
find
that steps of that W, right? W squares.
No,
I mean,
W's you find per choice of the hyperparameter. So actually, have you done 575 or no?
575.
Yeah, IDS 575.
No. I did.
You did?
I took that from statistics, right? Advanced statistics.
Yeah.
It's a business.
Yeah.
I did that by Professor Slack. He used to Stanley.
Okay.
He used to be very traditional way of teaching this thing. What do you mean exactly? Why you ask this?
Because cross-validation is about choosing hyperparameters. So W and B are just parameters.
Right.
So hyperparameter choice would be, let's say, the regularization parameter.
Right.
Let's say I think I wrote 10 choices, 10 to the power minus 5,
right.
10 to the power minus 4.
I know the hyperparameter is like irrelevant about the it's not WB, right?
It's not WB.
But it sounds like a...
It's the coefficient of the...
Right,
no, it's the coefficient of the regularization term.
Okay.
Now, exhaustive search just means for every value of the coefficient term, find me the best W and B, and then give me the cross-validation score for that W and B. And then you will find that for every choice of hyperparameter.
Just find them, so it's optimization, right?
And then you just find, it's basically...
I do understand a lot of terminology because this is like a new terminology for me. I mean, this word, so I mean, I know this.
Yeah, exhaustive search means just optimization by exhaustively trying out all options.
I just want to try to understand more about details of what you need to do. Okay, got it. So optimization.
Yeah, if you're getting confused, just ignore that line because just do cross-validation to find the best parameter of the regularization.
Okay, great. All right. Got it. Thanks.
Cool. When you are taking speech data, so you only have music, you don't have any text. So
yeah, it's basically...
What is the data type, like when you do Fourier transforms and convert it?
No, these are numbers, right? Even once your microphone picks it up, it's going to be... there's going to be some sampling rate of your... what is that, 44,000 or something, hertz or something.
Keep the frequency.
No, you just look at the magnitude of voice. That's temporal data. Now, if you do Fourier transform, you'll get the frequency data of what was the frequency in time. Was it high pitched or low pitched and all that stuff.
If we want to do our project and suppose use financial analysis, so what should we consider, like taking newspaper articles, blogs, or Twitter data? What would you suggest?
If you want to collect your own data, it's going to be challenging. But if you...
I don't want to
Yeah, then financial data sets, there are many, right? Try to figure out, like, narrow down the scope. Now you already narrowed down to finance. Try to see some example, 2-3 projects per choice that you said, and then see what's interesting, what's doable, what's sellable as well, and things like that. So, yeah, you'll find 2-3 choices for category that you mentioned. Yeah.
So in this particular example, if you see, like, you take 4 vectors, right? I mean, if you see for the hidden layer, we'll take only 3 weights, right?
Yeah, the number of
Why
weights
is
happen
it
to be
like my n minus 1 or something? What
No,
will you take?
your
Is there
choice.
any
You
intention?
choose.
Okay, fine.
It's a choice.
I thought because I saw the pattern here, so I was like, is there any reason?
No, good point. There is no choice. I
Because
mean, there
always
is no
like,
choice.
when we work on these stuffs, as you said, we keep trying with different layers, right?
Yes.
Figure out.
Yeah.
When I saw this, I thought, okay, something, is there anything?
No, unfortunately.
Clarified.
Okay. Yeah.
I just want to ask you since we are finding assignment 1 so difficult,
Yeah.
what do we do for the project?
So we are just 2% team.
So can we both join another team and make it a 5? Or
Because we are doing the assignment.
Make it 5.
yeah, I mean, like, just
There
can be
are
one
no
team
service.
with 5 people, or you want us to split
There's really no other 2% team?
the number?
Everybody is 3, exactly. Okay, I'll just check, and if there's 2% team, just join that.
There is,
Or if you-
like, we figured that, I mean, we asked the TA and she said she's looked at all the groups.
Oh, all 3. Okay.
Kind of don't know.
Is it difficult to do 2 people? I find it
Project the assignment itself is quite
No, but you have the advantage, right? You can do a little bit lesser and
I don't think that will work. I mean, the steps in a project will still remain the same, right?
No,
It's just
actually,
one
last time
less
what happened is
person.
people found that assignments are much more tougher than the project that they did. That's what in fact, yesterday somebody came and told me
You're talking about 576 or
576 assignments, but relatively more tougher than the project that they did.
So then-
Although the grading percentage was higher for the project and lower for the
So
assignment.
then maybe for assignment 2 we will still need a 3% each.
Sure, I mean, you can do whatever you want. I mean, within the constraints, it's fine. I'll accept it.
What would you suggest? Like, would it affect our grade? That is my only concern.
Yeah, if you make it 5, then you will expect a much higher level of project.
So that then becomes a problem for you.
Yes, that will become.
No one will want us then in their
Yeah.
Yeah. 4 is a little bit manageable, but I think I said something about like 0.75 times.
That's for the assignment you said. You said for the project it's fine.
Sure, you can do whatever. Don't worry about it. I won't penalize for like.
Yeah, because like we kind of don't have a choice. We started off with 3 and then someone dropped out.
Somebody dropped out.
Okay.
Uh,
Sure.
Okay.
Ideally, I would prefer 4-person teams. But
that's
5 is too much because now you really like if there will be project presentations and people will see what 5% team did, and if it's the same level as all the 3% people, then it's going to be hard to give the same grade. That's all.
Okay, let us ask around.
Yeah.
Who wants us?
Okay, so we will resume. Oh, I'm only 16 out of 92. Okay, people can see that. Okay. No, it's more than that. Okay, no. Okay, next we'll look at a variation of, now we looked at vanilla RNN. It really did not have much. It just had one hidden layer. And also somebody pointed out, why is H 3 dimensional? Has it something to do with the input? It's not. Here there was a choice made for the number of rows of W to be 3. Okay. Number of columns of W to be 7. Is that clear? It was just a choice of number of hidden neurons. I mean, how size of the hidden layer. Okay, so the next version, or a slight upgrade or a different model, is called again this should be probably here, long short-term memory cells. So basically the A cell is being changed to some other cell. Okay, cell or block is being changed to some other block. Okay. So here I'm just saying, the whole point is that there has to be some temporal dependence that RNN is capturing. So I want to illustrate why a vanilla RNN may or may not capture historical, previous information well. For example, if there are immediate preceding words like advanced prediction, then maybe the next word could be models if it's a word level language model. But what if you have a different case where somebody's there's a text blur where somebody says I went to UIC and then I lived in, and RN is trying to predict what the word is. Let's say Chicago. Then here more context is needed because there's dots. Maybe the first sentence was at the beginning of the paragraph and the last sentence is at the end of the paragraph. Then you need the context of UIC from a long time back. Of course, RNN is supposed to capture information all the way to the beginning, but it turns out because there's not much, there's quite a bit of restriction on the weights, right? It's the same weights everywhere, and so you're not able to really control what information it's capturing. Okay, so that's very empirical observation that I guess this is empirical observation that RNNs are not able to capture really long information long time ago in a nice way. They get overwritten, but that's a very bad word because there's really no notion of anything being saved to disk or any local variable, no memory as such. But the weights are tuned in a way such that you are kind of not capturing the features from features from long time ago. Okay, I mean this is just saying that if immediate preceding inputs are important, maybe the weights can be tuned such that it can capture that there were these guys, these words that appeared, and therefore I have to say models. Here, if there is UIC or something that appears here, and after a long time I lived in maybe you want to say Chicago here, then you have to kind of remember this, and that's kind of hard for the vanilla RNN to do because of lesser number of parameters, as well as there is no explicit control of what information is there's no explicit modulation of information as it's passing over from one step to the other. Okay. What do I mean by modulation? So I'm using words which seem as if I'm storing information and removing information, but it's really not the case. I mean, there are weights, all right? So at this point, there is some H vector, I guess H2 here, right? This H2 is the culmination of a lot of operations. Some x0 was concatenated with H0, I guess not H0 but H-1, which I guess is all zeros. So H2 is supposed to capture a lot of transformations and information that was there here. Okay, but as you move forward, let's say HT here is supposed to capture a lot of transformations and information from all these inputs. Okay, given that finite dimensional vector, there is no explicit control other than the weights, right? The W and B of the tanh, then hidden layer through which we are trying to kind of control what could be the activations here. Okay, for any test data. For training data, we want the activation such that we make the best prediction. Right? The control is not there. That's why for really context which is very far away from the current prediction step that you're trying to make, HT is, or the weights are not able to really ensure that HT captures that information. Okay, in the vanilla RNN. So to kind of fix that, there's this thing called LSTM cell which replaces the A block. Yeah, this is what I just said. They are not able to connect, or basically the HT is not able to capture long-term information for any test data point. Okay, even in training data point, it may not be able to recover with just changing W's and B's. You're not able to ensure that HT is such that you make the right prediction. Maximize the cross entropy. Minimize the cross entropy. Right. And LSTM, very handcrafted cell happens to, empirically, you can see, we see that it can capture long-term dependencies, and basically it's trying to avoid the issue with the vanilla RNN, which is that it's not able to capture long-term dependency. Okay, and so it has a similar structure, but it has a lot more components going on. So, but there are, I guess, people have after kind of familiarizing with it over and over, they have kind of given names to what's happening with each part of this cell. So LSTM cell is very similar to a vanilla RNN cell. Okay, the A cell is different, and instead of a single neural layer, they have 4 neural layers. Okay, so they've increased the number of parameters now. There are 4 neural layers. Okay, which is gonna control information as it passes. Control information, but now you have 4 parameters to tweak to, such that the right information gets passed on when you train using training data. Okay, so that on the test case, the right information gets passed on. Okay, again the same notation. I guess pointwise operation is something I missed. That's going to be in pink. Okay. So what are these 4 neural network layers in this LSTM block? So now there's going to be a slight change. There's going to be a different vector CT that's going to keep getting multiplied or keep getting transformed as you unroll. So it's the same RNN, right? So instead of just HT as before in the vanilla RNN, there's going to be HT and a CT. Okay, and CT is just nomenclature is cell state. It's just another vector. Okay, it's related to HT in some way. We'll see that, but another vector also being passed on. It's not related to the output, but it's something that gets passed on from block to block. Okay, now. So this is cell state. So basically, there's a from previous cell you get a CT -1, and you pass CT to the next cell. Okay, some operations are happening here. I'm going to explain that pretty soon. Yeah. So here I'm just saying CT and HT are CT and HT. I guess HT is not in bold, but CT and HT get passed on from cell to cell. HT itself is output of the cell. And there's an XT which is the input of the cell, same as before. These two are the same. Now, so in the unrolled network version, it's just this is supposed to, at least people are interpreting this vector to capture information. Okay. Capture information in addition to HT. HT was supposed to capture information, long-term dependencies. Now CT is a vector which we are going to focus on to try to capture long-term information. Okay. And yeah. And so really what we'll see is that HT is just a simple, I guess, let me just write it this way, simple transformation of CT. So our focus now will just be CT, because HT is just a simple transformation of CT, which I'll show soon. Okay. So the first, okay, there's this notion of gates. Okay, let me just see. Yeah. So there's CT vector that we need to kind of play with. The LSTM cell can add or remove information. Okay, this is just interpretative. This is just interpretation that CT is a vector. We can somehow change the coordinates. There are a bunch of numbers stored there. We can kind of add or remove information, as in basically change these numbers in these coordinates by regulating what are called gates. Okay, so this is again a nomenclature, and what these gates do. So these gates are somehow related to. Are going to be related to XT and HT -1, just like before. So in the vanilla RNN there was just XT and HT -1. Here also there's going to be HT and XT -1, but these gates are now going to be somehow related to these two inputs, and they're going to control the information, as in somehow change the coordinate numbers in this CT vector. Okay, that's the interpretation, that somehow you need to set these weights. There are 4 neural network layers. Somehow you set the weights such that for any test sequence, the impact is that these gates are essentially controlling information of context. Okay. No, it's different weights. Yeah. So what are these gates? So gates are basically made of a sigmoid neural network layer. So instead of TANFs before, there was one. Now we'll have multiple gates, and these each gate is going to be like this. It's going to be. I mean, I said the neural network layer. I'm going to represent as a yellow block. So the nonlinearity is represented inside the block. Okay, and there'll be pointwise multiplication with its output. Okay, so what is a gate? So I don't know how many. Is anybody did undergrad in electrical engineering? One. No, several actually. Wow. So do any of you guys remember gates?
Yeah.
Computer science actually. People have looked at what are those called? Truth tables. Yeah, logic. I don't know. It's not really logic as in math logic, but logic gates. Yes. So gates are somehow control. Like an AND gate will control whether the second input is going to go to the output or not. Okay. So here a gate is basically a neural network which is sigmoid layer, and it's going to kind of do a pointwise multiplication with a vector. And you can imagine this vector, since I've drawn it horizontally, is related to the cell state. It's roughly saying if there's a vector. Actually, I have a slide here. Roughly saying, let's say U is the input to this gate. So this is the gate operation. U is the input. Okay, some transformation happens, sigma, right? In fact, you can imagine that sigma is just because of this sigmoid nonlinearity, the output vector, whatever be the input vector u, the output vector is always going to be between 0 and 1. Remember, sigmoid was always output was always between 0 and 1. So it's like let's say u was -5, 10, and 15. Okay, maybe not regular like this. Okay, something like this. Maybe the output is and it's not just a sigma operation on u vector itself. It's going to be there's a W matrix there, and so this vector times W plus offset passing through a sigma nonlinearity may give you some information like 0.1, 0.2. Yeah, maybe that's it. It's 2-dimensional. Let's say output is 2-dimensional. Now these numbers are between 0 and 1, and then whatever the V vector is, it's going to be element wise multiplied. So let's say V is 26 and 5, then the output f of uv is going to be 2.6 and 1, right? So it's just element wise multiplication of whatever is the output here. Okay, there's the w and b here, and so this is a complicated operation happening, but it's just saying given a vector here and a vector here, this is going to be basically this vector passing through this hidden layer. Output is going to be whatever the hidden layer output is. Okay, whatever the size of the hidden neurons, number of neurons here is, and then you just element wise multiply. Okay. And that's what a gate operation is. It's not. I mean, that's a word that's not used here. No, we are not talking about any tuning yet, right? So let's not worry about tuning, right? It's just saying, it's like, so in the previous slide or the 2 slides ago, I said we want to control information, control what gets added and subtracted to the cell state vector. So what roughly gates will do is try to scale the cell state vector or do something else. Do something else to intermediate values which will be added to the cell state vector and so on. That's all. Regularization means something to do with preferring certain particular weights or bias vectors, certain weight matrices and bias. Those are the parameters. Yeah. Was this slide different from the previous one? Okay. Yeah. So basically the idea is determines how much of each component to let through. So how much of each component of V to let through. So in the previous example, only 10% of the component of the first coordinate of the V was being let through, and the second coordinate 20% was being let through, roughly. Interpretation, okay? And 0 of course means don't let through anything, and sigmoid will let you do that, go all the way from zeros to ones, okay? So ones are like your OR gates, it doesn't matter, once you set the second input to ones, it doesn't matter whether it's 0 or 1, it will get passed through. And yeah. So LSTM has 3 gates to control the cell state. So ultimately all this is about kind of ensuring that you have more degrees of freedom, these weights of these different hidden layers, so that you can interpret the cell state vector, which is essentially somehow capturing information from previous observations, previous cells, so such information can be updated properly, okay? And so let's look at, and each control has a I guess interpretation. So first is forgetting old information. So we want to kind of forget the CT minus 1, some parts of CT minus 1 or some CT minus 1 from before. So okay. So the forget gate. So again, I want to also point out that this U for us will always be, I guess most of the times will be xt and ht minus 1. Okay, maybe I'll have to check the blocks, but for us U is going to be something like this, and we sometimes it will be cell state, so something like ct minus 1, eventually giving us ct. It's not exactly this, but this is the interpretation. Okay, so let's think of the forget gate. It tries to change ct minus 1. Okay, so we want an output vector which is entries in 0, 1. Okay, and we're going to do element wise multiplication with ct minus 1. 1 just corresponds to keep the whatever was the cell state before, and 0 means get rid of it. Okay, and here's an example just to motivate what you need to forget. If you want to predict the next word based on previous words, cell state may include things like gender of the current subject in the sentence. Okay, this will be useful to predict, for example, he or she, for example, if you remember the gender or equivalent feature related to gender. And so when a new subject is observed, you kind of want to forget what gender specific information that you had before. So the CT should not carry, so basically CT is like maybe you encountered something about female, so you kind of remember the gender. Next word should be female specific words, and then some other subject entered into the picture, then you kind of have to forget something, right? So so we have more degrees of freedom to kind of ensure that this happens for test data. Okay. So the operation is here, concatenate, and so this I've shown it so many times, and then you do. So this is the forget. This is the forget vector, and it's going to be element-wise multiplied with the ct minus 1. Okay. There's some element-wise multiplication happening here. Next, forgetting done. Now new information. Yeah.
We were trying to retain information by introducing cell states.
Yeah.
Now we're trying to
Forget parts of it, right? It's not completely forget. It's not a single scalar value multiplying it with the cell state. You may want to forget some parts of it. Maybe you want to remember the context. This whole text was about Chicago, related to Chicago, but you want to kind of forget the first subject was probably female, then the next subject was male, then you want to kind of forget gender specific information. This is all interpretation.
So we are applying the gates there and
Yeah.
the concept probabilities. So how will you forget vector like this?
What is it?
Forget some subjects. I'm trying to understand.
How will it? Choice. The only degrees that you control is the weight vectors, right? I mean, this is architecture interpretation of you controlling the weight such that information can be forgotten or information can be added. Okay, we'll see. Is actually okay. Let me do this. Some error already. We'll see. So okay, this I could have shown earlier. So I guess a neural network would be, this is, I'll post this link on Slack anyway. So this is, this is the input, who identifies this particular Pokemon? What is it? Yeah, I know that. I was just checking. Yeah, this guy probably is. In fact, he quips about this blog saying that he could have caught 100, Pokemons rather than writing this blog post. But okay, so a neural network would be just looking at this image, trying to say something about probably the Snorlax is showering or drinking water or is being attacked, right? So RNNs would be like, okay, the previous image was another Pokemon. What is it called? I don't see the name here, so I don't know. But yeah, so given this, actually maybe. Oh no, this is not zooming in. Okay, so here you can see that this probability of Pokemon is being attacked is increased. Okay. Probability of showering is decreased. Drinking water is also, I guess, less. But it hasn't increased that much. And here you will see that it's being attacked has increased more. And the last one is actually LSTM. So here actually there is a textual description of what's being retained. The only problem is it's not zooming in. So let's see. Yeah. So in RNN, actually there is no forgetting notion. So there's a bunch of information. So it's only, and it's a finite length vector. So you kind of want to, which parts to remember all the time. Here you want to, there's some textual description saying, Snorlax likes bamboo. Not bamboo, sorry, whatever. 1 minute in the battle, enemy in the center of the screen. Okay, working memory is a subset of this, of your memory. It's not really memory, these are all vector representations of what's happening in the images before. Okay. And then in LSTM you basically want to kind of say what should I forget, any Pokemon's location on screen, at this point. What should I say? It's not like look of pain. What should I ignore? It's not like directed preferences. Some interpretable changes that you want to do to the memory, which includes forgetting, adding information and so on. And then what gets stored in long-term memory, still there is this information. And then some new information, so like hit by water, in pain, and working memory will be a subset of that. So forget about working memory. All I'm saying is LSTMs are more descriptive, but can capture aspects which will lead to a better conditional probability of what's going on, in the scene. This is just the illustrated thing. It's not really, it's not an actual implementation, but to just illustrate.
We apply forget factor to the CG vector. So initially only we forget it and then we apply the gate again.
Yeah. I'm just explaining this in a sequential way. All these operations are happening at the same time. There's no one step after the other. So forgetting multiplies CT minus 1. There's some other parts which are multiplying at the same time to some other things, and things are getting added. It's just an expansion of explanation of a graph, computation graph. Okay, that's what I'm doing. Okay, where was I? Okay. So that's about forgetting. We just element-wise multiplying with CT minus 1, and hopefully it captures forgetting aspect of the problem, of this information, that long-term information that we want to store. Next step is deciding what new information we will get to store in the cell state. Okay, we'll just decide what new information we want to add. For that, there's going to be two things. There's going to be a gate and the usual Tannish layer. Okay, the gate decides which values to update, which values of the cell to update. Okay, and the Tannish layer creates a vector of new values to add to the cell state. Okay, that's going to be called C tilde. So two things. One, I need to decide which values to update, which coordinates to update, and what to update with. Okay, and that's represented by this part of this block. Again, everything is driven by just ht minus 1 and xt, just as before. So this would be the usual, tan h operation. Okay, so this will create your c tilde t. Okay, this is what you want to finally update ct minus 1 with. But there is another gate, again multiply, again the sigma hidden layer, which is gonna do element wise multiplication with c tilde to say, there is new information, but how much of certain new information should I retain, how much of new information I should forget, in the sense of not add it to my cell state. Okay, that's the and again in terms of just network layers, it's just concat ht minus 1 and xt, add appropriate biases and appropriate nonlinearities. Okay, the gate operation is kind of what we saw again, and it's the same, but we're just calling it input gate here. Okay, and then once we control c tilde t, we control it with the input gate. This is the input gate. We just add it to ct minus 1, which we have already forgotten some parts of ct minus 1 because we kind of did something here, and then there's a rescaled, coordinate wise rescaled ct minus 1, which we are adding something here, element wise. That's how. So in the language model example, add the gender of the new subject to the cell state, for example. That could be an interpretation. Okay, it's just an interpretation of, we want to set the weight such that these things happen in training data as well as test data. And last step is modify the cell state, which I just said, element wise multiplication of the forgetting gate, and I guess, yeah, I just said this. I mean, c tilde is multiplied with the input gate, and then you add that to your cell state. So previous cell state is you multiply element wise with the forgetting gates outputs, and then you add with the new information. Okay, that's your new CT, and just pass it to the next cell. That's it. Forget and add. And so, as I said before, CT is our new HT. So now HT is just going to be some simple transformation. I think I said. So in this case, output, since we want to kind of have a function between HT and CT, the natural choice is again a hidden layer. Okay, again a neural network layer. In this case, we're going to pass it through a Tanish layer, and we'll also have a gate. Okay, and this gate is just trying to decide what part of cell state will output. Okay, so for this side, actually, yeah. So cell state is here. This is CT, right? This part is CT. That's going to go into a Tanish layer. That's shown in a blob over there. And then again, the gates always controlled with HT minus 1 and XT, which will do an element-wise multiplication with the outputs of Tanish layer, and that's going to be your HT, which is going to be ultimately shown to the. Ultimately, is just designated as the output. Okay, it's a transformation of CT essentially. It's a nonlinear transformation of CT because of the Tanish nonlinearity, and some rescaling because we can do that rescaling. Okay. Yeah, and because we don't want, otherwise HT minus 1 would be just CT. If you had just connected directly, that would be another alternative. But so this is just hand designed LSTM, which with all these interpretable components, which happens to do better than RNNs in capturing long-term information. Okay, so just a summary. So there are 4 parts. Forgetting. This part is adding new information. I guess not this one. For getting new information, adding them both to the cell state, and then using the cell state to define HT, right? That's this part. Cell state as well as these guys to figure out HT. Okay? Forget and remember, modify the cell state with forgetting and remembering aspects, and then give an output. Okay, so that's LSTM. Any questions about this architecture? There are a lot of processing, and there are basically 4 neural net layers, right? There's this 1 sigma here, 2 here, 2 here, actually 5. Really 5? Okay, 3 gates and 2 tanh layers. Okay, 3 sigmoid layers and 2 tanh layers. Okay, with different weights, all of them. Actually, I think this is not a layer. Maybe it's just element-wise tanh operation. I am sorry about that, but we'll check. I'll clarify that later. But I think because they put it in pink, probably it's just element-wise rescaling of the input. Okay. Any questions about LSTM? Yeah.
Does this architecture also capture information like let's say we have 2 paragraphs. In paragraph we have information possibility very and there's another paragraph which are like where information is near each other. So would we need 2 different LSTM for the LSTM of 2 paragraphs, or would these 2 paragraphs would be interpreted as one LSTM itself?
No, this is just a cell, right? So this cell is just basically a replacement in the vanilla unrolled RNN that you had. Now whether that RNN captures information across paragraphs or information within paragraphs.
I'm just taking an example of paragraphs just to set 2 different things. When let's say there's one sentence which information is pretty early
Mm-hmm.
and another sentence is saying information is pretty early.
Yeah.
So will it capture both the sentences and the context of the sentences?
It should. If the training data has things like that, where context information is closer to make the prediction, as well as training data has training sequences where context information is farther but is relevant to making the right next prediction, then your LSTM weights of all these neural net layers will be set so that you kind of cater to both settings, right? Also, the same thing as vanilla RNN, all these weights are tied, it's the same weights across all the unrolled blocks, okay? And there are also variations. There's also variations. There's also another variation which is popular called gated recurrent unit, which is a different block. I'm not gonna, given that we went through LSTM and there's so much information there, so, but it's really not, not complicated, but it just has more information. So similarly, there's another variant called GRU, which is also famous. Okay. So these guys were actually invented in 1990s, I think, early 1990s, or maybe late 1980s. How many of you were not born in late 1980s? A lot of you. But anyway, so these things are invented. So these are as old as you probably. All I'm saying. Okay, so they also have. So there's another version called GRU, which is also famous and which does well in the sequence learning tasks. So remember the slide where I had one classification towards the left side and then 3 other tasks, right? So GRU happens to also work well, along with LSTM. And these are the update equations for that. So LSTM, essentially, if you did not want this interpretation, LSTM has an equivalent 4 set of update equations of going from HT-1, CT-1 to HT, CT, and that's it. So that's what it is. But we just added interpretation to kind of understand what it could potentially do compared to a vanilla RNN. Okay. What are the applications? So we'll look at several applications soon. For example, somebody mentioned speech to text. You can use LSTMs. Machine translation, you can use LSTMs. Anywhere where you use RNNs, you can use LSTMs. And where do you use RNNs? Like video captioning, image captioning, all those tasks. Sentence classification, you can use RNNs, and therefore you can use LSTMs. language models, you can use RNNs and LSTMs, same thing. So let me just spend like 3 slides on other variations of RNNs, and then I'll actually go into examples in a little bit more detail rather than just words. Okay. So one variation is, these are blocks, so you can actually kind of keep stacking them as Lego blocks on top of each other. So here is your vanilla, here is your RNN, just a linear one. At one level, you can actually take the H's and call them X's and add one more RNN on top. Okay. So now you have, so let's say you are scoring here, then you have gradients which are passing, all over a lot of paths like this. So if there is a W here, and maybe the same W here, you really have to take into account all those gradients. Okay. So this W is participating in the scoring of this guy, and so on, all the way till here, all the scoring of all these outputs potentially, right? So there's a little bit more complexity here. The computation graph has doubled. Okay. You can add more layers if you think it's useful. It's actually not very useful, I think. Yeah, maybe in 2015 it was useful. 2018 maybe not. I don't know. And people are, people keep investigating and kind of publishing new architectures or variations of these recurrent neural networks. And somebody actually has, I guess, so this 2015 paper is actually really covering, from the beginning of LSTMs that were proposed in the late 80s all the way to 2015. They've tried to kind of really say which architecture actually really captures this long-term information to do well on these tasks that I mentioned, okay, these applications. So, and I guess the output of that survey or exhaustive search was that the LSTM that I described in the for the past 10 slides, and GRU happened to do well. That's why we are studying that. Okay. Training, that's what I've been mentioning so far. Most operations are differentiable, so you basically define appropriate loss. For example, in the toy example we had was the addition of the cross entropy losses at each output. You just to run back propagation, all you need to take care of is that gradients need to be added. Okay, and that's what happens behind the scenes if you run an LSTM in TensorFlow or other packages. Okay. Any questions here? There's a couple of example codes from from Keras, and TFLearn is a package on top of TensorFlow, just like Keras. But if you want to study at the level of TensorFlow, the TensorFlow examples also has a sequence-to-sequence learning tutorial page. You can look at it. On Keras is actually quite short code, so you would think that it's a very easy thing. So here actually they're just doing movie review classification. So you have a review blurb, which text blob, variable length. Actually you can maybe even make it same length. In fact, they do that in this code, and then you just classify whether it's a positive sentiment or a negative sentiment. Okay. I don't know. Okay, we'll not see the code, but I will post the code because I just closed my connection to my server there, so to open the browser. So we'll see it later. Okay. And here is just one final look at LSTM where we have explicitly drawn the dimensions. So let's say input is 2-dimensional. Okay, xt is 2-dimensional, and cell state is also 2-dimensional. That is actually showing you that the this forget layer, so forget gate will be 4-dimensional because HT, also HT is also HT is 2-dimensional, so they get concatenated. So this is 4-dimensional here, and the output of the forget gate is going to be the same dimension as the cell state, and so 2 lines are drawn. Okay, so this is just an explicit description of what is the dimensionality of each vector that I was talking about. And so if this is 2-dimensional, this is 4-dimensional, then the W matrix is what? Has 8 numbers, 2 rows, and 8 columns. Okay, this W matrix here has 2 rows and 8 columns. Sorry, 2 rows and 4 columns. Yeah. And there's another B vector which is 4 dimensional. Yeah. Similarly, you can compute the other things. I mean, they're all the same dimension actually. Yeah. This actually happens to be element-wise Stanish operation, not layer there. Okay. So there are only 4 layers, 4 W, B pairs to be updated with your training data, whatever the task is. If it's IMDb review classification, then that's what you do. Okay. Any questions about LSTM? I know I've been asking questions, but yeah.
Clarified last time. It was element operation, was not the layer.
Mm-hmm. Mm-hmm. Yeah. So actually, yeah, the last step is you just want to modulate what part of CT you want to call it HT as an output. Okay, it's basically just saying element-wise information that you actually want to show as the output now, if HT is considered output. That's all. So that modulation is happening by this layer, I guess, output gate. So there's an input gate, there's a forgetting gate, there's a new information gate, and there's an output gate. 3 gates. And the original TANH is the original TANH non-linearity layer already present as in the vanilla RNN. Okay, so now we'll look at some applications and not go into the details of the blocks. That was kind of gory details, I would say. Okay, so let's look at a few examples. I think we have quite a bit of time. Okay, so the first example is actually sentence classification. So this we have actually seen. Sentence classification, remember we actually even went through convolutional neural network model for sentence classification as well, where we organized the sentence as a matrix where we encoded the word as a each row of the matrix was a word vector representation. It could be even the vanilla, I guess, one-hot encoding word representation, or it could be a embedded word representation. Okay, so here I guess it's very clear that sentence is just going to be sentences words or word representations will be passed here, and ultimately you only care about the scoring of the final output. Okay, so here you can, for example, you can have a cross entropy loss which just depends on a rescaled version of HT. So you can just consider HT as scores and then just do cross entropy definition there. So that's it. So sentence classification, we're really not spending much time. The next, first interesting example is image captioning. So image captioning is where you can use CNNs and RNNs together to go from one data type to the other. And the way you'll do it is, so you have images, you'll use a CNN to get basically a feature representation or embedding of the image. You'll use embedding of words. Okay, not here, but yeah, you can use embedding of words, or if it's not needed. So basically, you start with the feature embedding of the image as your starting point, basically h-1, or in LSTM's case C-1, the cell state -1, and then just do the just perform the RNN operation here. Okay, so the RNN has to generate a caption. Okay, which means that looking at the image, it has to, given the condition on HT-1, it should be, at least in the training data with images and captions, you want to ensure that given that image, the first word happens to be, is close to the training data first word caption, right? So that hopefully in the test data for a different image, it generalizes in a sense. If in test data, if this is the image, then maybe the first word has to be straw. Okay, hopefully the training data has many images and many captions such that the weights are set for your RNN such that this can happen. Okay, that's the idea. So you have this image, maybe this is CNN will generate basically a image embedding. So this would be, in this case, the 4096 dimensional. So I think this is VGG16. So I'm taking not the last fully connected layer, but the second last fully connected layer. It's 4096 dimensional vector. So that would be the image embedding. Okay, and then I'm just gonna pass that image to my RNN cell. Okay, and starting my initial X naught would be just some starting token, some starting symbol, some vector, doesn't matter, fixed vector. And then you are trying to ensure that Y naught, at least in training data, is the actual caption's first word or the word's representation. Okay. You wanna so you remember this output is supposed to be the dimension of the vocabulary of English language. So you really have a really huge cross entropy. Yeah, it's just the denominator has like a summation over a lot of terms. Okay. Yeah, basically. Yeah, here I'm just showing that there is an input which is also depends on the image embedding. If you think of it that way, the first cell will have a slight modification like this. Okay. And then, so ideally, what you will actually get is a distribution. Maybe it's not continuous distribution, but it's a distribution over words, right? Some words are more likely. These are going to be the transformed version of the score vector. You can sample one of these words. You can sample from this PMF over this vocabulary. You'll get a word. Okay. You can take that word as a starting point, as a XT, the X1 for your next run of your RNN, as the input to your RNN. The cell RNN cell in the next step. Okay. Basically, let's say in this case, I'm conveniently showing that straw is a sampled word. It could be something else. Yeah. So why did I do sampling? Okay. That's only because I was illustrating it for the test data. Okay. In training data, you actually have these Y's. So you want to ensure you will have a cross entropy loss, which shows that there'll be a Y with one coordinate high, and you want to kind of match it, and that's what cross entropy loss is doing, right? Here for a test image, you really don't have any reference, of course. So you're sampling from whatever is the output conditional probability that you're saying the class could be the word could be at this current point. Okay. Yeah. For CNN, no, you're talking. CNN is all. Let's say it's pre-trained. You downloaded VGG16 and you got the representation of the image. That's it.
Okay, so we have final scoring probabilities.
Yeah, for a test image, for the first, let's say so I'm telling you the operation that's happening once you already trained the weights. Already trained the weights of the RNN. So the weights, if let's say we are using LSTM, there are 4 layers, right? So 4 weight matrices and 4 bias vectors. You've already trained, and now I'm telling you how to generate a caption, an example caption. I mean, how you generate an example caption with test data. It's just the additional vector. This vector. In this case, it's a photo. It's just an embedding of the image.
You said based on higher scoring instances strong.
During training, forget about sampling. During training, you already know what our caption should be. You have an image and a caption pair. That's your training data. Right? It's sequence-to-sequence learning, so you need to have inputs and outputs. So you know that for that image, the first word should be, let's say, straw. If it was in training, then you have a cross entropy loss for this part, which will say if it's not straw, then you're penalizing the choice of your W's here. And then you're not sampling actually, you're just copying the straw here, and that's the second input. During training. But during tests, you sample, you pass it through your block, and you get previous information that will give you a different distribution over the word vocabulary. Different distribution here, and then again you sample, and so on. And you sample. Hopefully, you sample end soon. Otherwise, you'll keep sampling and generate a huge caption. Or you can also kind of stop sampling after some length. Okay. And this is ideally what we want to achieve with the automatic image captioning. For any test data, somebody needs, the computer kind of spits out a caption for what's happening in that image. And you can imagine what we can do with just, you can caption images, you can also caption sequence of images, you can caption videos. So you can find, computer itself can tell you what's happening in the computer, or AI system can tell you what's happening in a video, right? That's the goal. Okay, any questions at this part? All we did is just add a image embedding into the mix. That's all. Okay, the third part is just what is called auto replies. Okay, and with email apps these days, there's an auto reply. I think one of the email providers actually provides suggested replies that you can reply, right? For any, Yeah. Does any other vendor also do that? LinkedIn. Okay. Okay. So, yeah. So here basically again variable length inputs. In this case again text example, and variable length outputs. Okay. So previously it was not variable length. It was fixed length input. The image embedding, image is the input, right? Image is always, let's assume it's always 1000 cross 1000 dimensional. Then it's a fixed length input, variable length output caption. The third example is about variable length input and a variable length output. So even machine translation, like if you want to translate from English to Spanish, variable length sentence in English and a variable length output in Spanish, right? So all these other guys like question answering. So you can actually make AI systems answer questions. So if you have a lot of huge database of questions and answers, maybe from that it can learn the domain and can answer some of the questions. And this is very useful in maybe in contact center or call center settings where there's a restricted domain. Maybe it's a telecom contact center. Then new agents can get prompted on what are the likely responses or something like that. It's a pretty practical thing. Same thing with translation and transcription services, summarization of text and translation, as I was saying. So okay, let's focus on auto reply. Basically the computer reads your email, okay, that you need to agree with, and then it responds appropriately. So I guess this is the responses here. And so how does it work? The first version is as follows. Okay. So again, it's an LSTM. So we want to start the response only after we have read the whole input. Okay. So we pass. So at least during training, we'll pass our inputs. Hi, how are you, and whatever, a lot of things. Ultimately, and then start scoring with respect to maybe cross entropy loss. That this is the word. It's not really a word, but let's assume the vocabulary is there. Then ensure that this is the word that comes here. This is the word that comes here. So those configurations of these weights in these blocks, such that these words are the ones which have the highest, which lead to the lowest cross entropy. Okay, aggregated cross entropy, for example, right? So that's basically what you do. And here it's the same as before. You kind of I'm going to be okay. Here actually there's no. Okay, in this first version there's actually no feedback here, so it's just some same weight matrices, and I'm just outputting the words. Okay. Yeah, this is something that always true. In the second version, I'm saying, okay, I'm going to think of this part as an encoder. It's encoding the whole input email as some vector here. Once I've read the whole input email, there is the cell state or whatever HN, is going to somehow have information, context. In this case, the whole email is context. And then I'm going to respond. And response is very similar to before, except that I'm now adding the first response. At least in test time, I'll draw a sample from the output probability distribution over my vocabulary, and use that as an input. Take some information from here, sample another word from my output vocabulary, and so on. So this was the version we were anyway looking at image caption. So let's think of this as the right version. So this is like a decoding of the context. So you got the context encoded in a vector, the last vector here, and then you're decoding it into a response thing. So yeah. Yeah, so in training, during training, you actually feed back each true output. So whatever you predict here doesn't matter because it's going to be cross entropy based scoring there. But you actually predict the true response that you're supposed to give for that email. So you need to have that database, okay? Which people have millions, thousands of emails which they never delete, especially with cloud-based email providers. So you have lots of information even for a single person. So a very personalized solution. Okay. Yeah, so during test time you can actually do this. A variation which is somewhat suboptimal is that given input sequence, we first output something, which in this, in the image captioning I was saying sample. You can actually just output the one which has the highest probability, the word which has the highest probability in that vocabulary size probability vector that you get, and then that would be a word since you chose, that's the next word, and given that word you can output the next highest probability word for the next step and so on. Okay? So you can just go with highest probability, not go with the sampling business. Okay, but this could be greedy in the sense if the first word is wrong, then all the subsequent words get wrong. So what people do or have suggested is to actually track multiple candidates for the responses that you want to kind of generate and keep rescoring them. So that's called beam search. Okay, it's just these are the intricacies that you'll get into once you get into any domain. So in this case, it's auto reply problem that you want to solve. So the beam search is just saying, let's say there was an email input. I want to pick the first word. Let me pick the top 3 highest probability words rather than sampling, because sampling will really, maybe even say end, that's it. Right? I'll pick the top 3 words and then keep track of, given this word, what will be the next words? The next words I'll generate. Given this word, what's the next word I'll generate? But again, track of the next 3 words, best 3 words. Okay. And then what I'll do is beam search, otherwise, this thing can keep exploding, right? At every node, at every response, every word I'm saying, I'll keep track of the next 3 words. Okay? So I'll get huge tree, right? Ternary tree. So instead of that, beam search says, okay, you maintain some bunch of candidates, maybe 10 candidates. Okay. So at this point, you have 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 candidate replies that you could give. Maybe you can trim that to have only, let's say, 5. Okay, you can delete some of these paths. How will you delete them? By just multiplying the probability of this word times this word. You just remember that, and the joint probability. You will see that the joint probability of some of them will be lower than the other. So you are basically not immediately greedily ignoring other words. So you are willing to consider a little bit less likely words so that the response is better. Okay. It's called beam search. You might have come across beam search in some other settings. Okay. Beam search decoding. Okay. Yeah, there's yet another issue, but we will not fix it here, and that's because now we're already like too many tricks in the hat. So the link between the input email and the output email is just just one link here, right? The reason why I'm going to that is because I can't really write black on black, but okay. So there's this one link here. Change the color, I agree. So there's this one link here. So whatever be the email length, whether it's 10 words or whether it's 2 pages of somebody wrote something, it's all encoded in one small vector here. This is a little bit unsatisfactory, right? Because the hidden layer, the cell state dimension is fixed. Okay, so you can fix it with what is called an attention mechanism, or basically saying that you can add a few more neural network layers in some other way so as to kind of get rid of this handicap that it's a fixed length vector, irrespective of the, for variable input, variable output settings, you may want to kind of, people have come up with some add-on neural network layers which take care of the issue that this is a fixed length. But we'll not discuss about attention now. But it's an interesting technique. Do you guys understand what the issue was? No. The issue was if you had a small email or a long email, there would be one cell state here. It's a 100-dimensional cell state here. So 100-dimensional cell state can remember context for, let's say, a 100-word email, but a 100-line cell state may not be able to remember the context for a 1,000,000-word email. Right? So that was the issue. And so there is some additional neural network layers that you can add, not on these blocks, some additional things that you can put so as to influence the choice of the first word, and that's called attention mechanism. So it's basically, since you have more parameters, you can do something better. Deal with this arbitrary variable length input issue. That's all. Okay. Finally, speech person. So this is speech transcription. so in speech transcription, basically speech to text there are several models in speech to text. They are pretty modular. The first model is called the acoustic model. It's basically saying, given a word, what is the sound that's produced? So think of output as like the sound, and how do you measure sound? Using a microphone, you'll get some waveforms. So that's how, let's say that's the output. The question is, what is the probability of seeing a certain waveform given the word, and given the speaker is somebody? Let's say, right? So that's called the acoustic model. People build these models using what are called Gaussian mixture models. But we'll see them in if we see them. Actually, mixture models we've seen in 575, right? Some 2 Gaussian mixture models we've seen. So these acoustic models can be also modeled using Gaussian mixture models. Okay. In fact, they were the predominant technique. They are the predominant techniques of. I don't know how many of you have seen this software called Dragon. Naturally speaking, this used to be there before Cortana, Siri, and so on. So they were based on these types of technologies. Anyway, and then the second model is actually the language model. So remember the language model, we were just generating new text. It's not just for generating text. That's a fun application. It's to actually do, for example, speech to text, right? And these models, I think language model was based on Markov models. So that's what we saw a Markov-based language model, right? So this is an example there. And lots of feature engineering to do the speech transcription. That was the typical pipeline till 2010 or maybe 12. Now with RNNs, you can actually do end-to-end speech to text, and that's the same kind of formula that we saw before. Basically, start with speech signal. Okay, something like this. This is a waveform. Okay. You get some fixed length vector. So how do you do that? You chop the waveform. Maybe take. So this is a waveform in time. Okay, it's actually like a bunch of sinusoids. It's not really sinusoids. Yeah, overlapping sinusoids. Okay. You chop it into several parts. Okay. Maybe overlapping. So this was first block. There's another block here. There's another block here, and so on. Overlapping blocks of temporal signal measurements, maybe through microphone. You do a Fourier transform, you do a frequency domain conversion to that, and that's your XT. So XT would be, some frequency conversion of block of temporal. Wait, this is not right. Temporal signal. Okay, and given that, you just continue as it is. So in this picture, I'm showing you 2 levels because that's one of the families of RNNs, right? So given blocks like LSTM block or GRU block or even vanilla RNN, you can actually do multi-level architecture like this. Okay? And this is an illustration to say that you can do this. There are also variations called bidirectional LSTMs and so on. Let's not worry about it. There are many variations that people are proposing because these seem to have a lot more parameters and are able to do well in prediction accuracy. Okay, or all these tasks. So any questions? I think I'm almost done. Or yeah. For speech to text, people read. Yeah. For Sanskrit, I'm not sure.
I mean,
but Mandarin, yeah.
Sanskrit, but the languages that they write on.
Yeah, I mean, it's possible to train for Indian languages as well, but I don't know about speech to text, how much mainstream effort has been done, but I'm sure people have trained. I mean, there are decades of research into speech processing, right? So, yeah, people have done that. Yeah. Actually, for example, word to vec or word embeddings, right? I was only talking about English word embeddings, but I think Facebook AI Research has released word embeddings for like 60 languages. So you can actually just download these word embeddings and do your vanilla machine translation. Like if you get a sequence of words in English, you can do sequence of words in your own language, any of the 60 languages. Internationalization, like a cheap way to internationalize your website, maybe. So that would be very bad. But yeah. Any other questions? Okay, to summarize, there is a need for RNN. So sometimes actually Markov models are good enough, like the one we saw last lecture for like character level Markov model. But sometimes you need this because if you want to have context information. We understood the internals of RNNs and LSTMs, and we looked at some implementation details for, not really implementation details, but some little bit of more detail for some of the applications. Okay. Okay. Yeah, that's it. So today we ended the class early. Do you want me to explain word to vec or not needed? There was word to vec which was left from last time, but I think you guys are exhausted, so let's not worry about it. Any questions, you can come forward and we can discuss more. Yeah. Yeah, 1 second.